Hello, in this video we're going to talk about modeling with trigonometric functions. You will learn how to interpret and use frequency, how to write trigonometric functions, and how to use technology to find trigonometric models. First, a little bit of vocabulary. You may have heard this word frequency when it comes to things like sound. Okay, well, the definition of frequency is that frequency is the reciprocal of the period of the time over which something occurs. Okay, this frequency is actually the number of cycles per unit of time. So how many waves does the sound make within, say, 1 second or 1 millisecond? Okay, and it's important to notice that frequency is the reciprocal of the period. Okay, so we have the period as being 2 pi over b. The frequency is the reciprocal of the period, which is going to be b over 2 pi. Okay. The other vocabulary term that we need to know is this term called a sinusoid. Okay. A sinusoid is basically any occurrence that can be modeled with a wave type of graph. Okay, because we call a wave type of graph a sinusoidal function or a sinusoidal model. Okay, so you could think of this as your height on a Ferris wheel, where you get on the Ferris wheel at the bottom, and then as time goes by while you're riding the Ferris wheel, you go up to the top and then you come back down to the bottom, and then you go up to the top and you come back down to the bottom. You go up to the top and you go back down to the bottom over and over again, exactly the same. Okay, or you could think of it as on a bicycle wheel, where you've got the little stem to insert air into your bicycle wheel. As you're riding your bicycle down the road, that stem is going to go up and down and up and down and up and down and up and down. Okay, you could also think of this as the temperature. Say the high temperature of the day in Denver, okay, in January is pretty low, in August is pretty high. In January it's pretty low, in August it's high. In January it's low, in August it's high. January low, August high. And you get the idea. Okay, so let's use these to do some modeling. Our first example of using frequency, a sound consisting of a single frequency, is called a pure tone. An audiometer produces pure tones to test a person's auditory functions. It's a hearing test. An audiometer produces a pure tone with a frequency of 2,000 hertz. That's cycles per second. Okay, so 2,000 cycles per second. The maximum pressure P produced from a pure tone is 2 millipascals. That's the maximum. Okay. Write and graph a sine model that gives the pressure P as a function of time t in seconds. Okay. So when we're using sine, keep in mind that we're using y equals a times the sine of bx. I don't need minus h or plus k because we're not going to move this function to the left or right. We're also not going to move it up or down. Okay, so in order to understand the maximum is 2 millipascals, so that's going to go right here. So we are going to replace A with just 2. Okay, in order to understand the frequency, okay, the frequency is going to be B over 2 pi. Okay, we learned that in the last slide. So the frequency is going to be B over 2 pi. So I just need to take this 2,000 hertz equals B over 2 pi, and then I can multiply both sides by 2 pi times 2 pi, and I find out that B is going to be 4,000 pi. Okay, and then I can write my function for my model. That's going to be y equals 2 times the sine of 4,000 pi times t. And I should say that this is not y, this is the pressure, right? So this is going to be pressure based on time, is going to be 2 times the sine of 4,000 pi. Okay, so we're completing this wave. We're completing this wave in from this point 0, 0. Okay, our wave is going to go up, come back down, and then go back up. And this is going to be 1 over 2,000. Why is it 1 over 2,000? Because the period is 1 over the frequency, okay? Or the frequency is 1 over the period, okay? So since this is sine, it's going to go up to the middle. So it's going to hit the middle again, and this is going to be 1 over 4,000, okay? We're going to have in the middle right here 1 over 8,000. It's going to reach its maximum at 2. And then in the middle right here, this is going to be 3 over 8,000. And it's going to hit its middle down here of -2, -2. And then just draw your nice smooth sine wave. And know that this keeps going. Okay, let's look at this example. For this example, we are provided with the graph. We want to write a trigonometric function for this sinusoid shown. Okay, so the first thing that I like to look at is where's the top, where's the bottom. I see that this has a maximum of 5 and a minimum of -1. Okay, so those are our maximums and minimums. If I go halfway between those, I can find the midline right here. This is going to be the midline. Okay, and it looks like if I just count 1, 2, 3, 4, 5, that's my scale on my y-axis. So the midline here is going to be at y equals 2. Okay, so that's how far I've moved the graph up, right? I have shifted this whole graph up 2 units. That means that k is going to equal 2. Okay, and then I also need to look at the amplitude of my graph from the midline to the highest point right here. From 2, 1, 2, 3, I'm going up 3 units to get to the maximum point of 5. So that means that my amplitude is going to be 3. Amplitude is the A value, so A is going to be 3. Okay, and lastly, I need to look at how many of these cycles are showing up in my graph, right? How quick is a cycle happening? Okay, so if I go from this highest point of pi over 8 down to this lowest point of 3 pi over 8, that's half of a cycle. Do that again, and that's a full cycle. Okay, so I've got half of a period in 3 pi over 8, that's a 3, minus pi over 8. If I subtract those, I get 2 pi over 8. And if I reduce that fraction, I just get pi over 4. That's half of a period. So a full period, I just need to double that. 2 times pi over 4, right? And that's going to be pi over 2. Okay, that's my period. My period is equal to 2 pi over b. Okay, so pi over 2 equals 2 pi over b, right? We took notes about what period equals and how it relates with b in a previous video. So if I cross multiply this, I get pi times b equals 2 times 2 pi is 4 pi. And now I can divide both sides by pi. And I get that b equals 4. Okay, so I'm going to put all of these things together. We've got our amplitude of 3. We've got our shifting up, a vertical shift of 2, and we've got b is 4 in order to change our period length. So when we write our function, instead of y equals a times the sine of bx minus h plus k, I don't need this minus h, right? Because I'm starting at the midline and going up. So that's a perfect sine function. But I do need everything else. So this is going to turn into y equals, we found out that the a is 3, right? Times the sine of bx. So b is going to be 4. We found that. And then k, we found out that the midline is shifted up 2 units, so plus 2. Okay, and that is going to be the function. You can type that into Desmos and check it if you want to. Okay, Desmos is a great way to check your work to see if you're correct. Okay, so in this third example, we have modeling circular motion. Okay, if you've ever watched people play jump rope, whether it's 2 people turning ropes and then 1 person jumping in the middle, or 1 person holding onto their own rope, the rope goes up and down, up and down, up and down, up and down. And it's very repetitive like that, right? So this is a great use of a sinusoidal function. Okay, 2 people swing jump ropes as shown in the diagram. The highest point of the middle of each rope is about 75 inches above the ground. So that's where we have this. And the lowest point is 3 inches. So that's where we have this. Okay, so the ropes aren't actually coming down and slapping the ground. They're staying above the ground. The rope makes 2 revolutions per second. So that is actually in terms of frequency. We want to write a model for the height in inches of a rope as a function of time, given that the rope is at its lowest point when t equals 0. Okay, so first we're going to, in order to find the k value and the amplitude and all that good stuff, let's just go ahead and plot this, right? We have the highest point is going to be 75 inches above the ground. And the lowest point, it's not actually going to touch the ground. So the lowest point is going to be 3. So I want to find halfway between those 2 points, okay? In order to do that, I'm going to add them, right? I'm going to find the average, the middle, right? So for my k, I'm going to add 75 plus 3 and then divide that by 2. 75 plus 3 is going to be 78 divided by 2 is going to be 39. Okay, so the midline is going to be at 39 right here. Okay, that's going to be the midline. Okay, now we want to find out how far from the midline are we going to the maximum. Okay, well, that's easy. We have A is going to be 75 minus 39, which is 36. Okay, another way of doing that, if you don't know the maximum or you don't know the midline, you could take just the maximum and the midline or the minimum, and instead of adding them, you could subtract them. So you could do 75 minus 3 and divide that by 2. 72 divided by 2. 72 is 75 minus 3. And you still get your value for A, your amplitude of 36. Okay. And then we want to talk about this thing called frequency. Okay. frequency, if you recall from just a few minutes ago, frequency is the same as 1 over the period, which is going to be b over 2 pi. Okay, this has a frequency of 2 revolutions per second, right? So 2 equals b over 2 pi. I'm just going to multiply both sides by 2 pi. And those cancel so that I find out that b is going to be 4 pi. Okay, and when I put all these together, I've got the value of k, the value of a, and b is 4 pi. Okay, those are going to help me write a function. So we've got y equals 36. I'm going to use cosine this time, but that's because the rope, it says in the last part of my problem, the rope is at its lowest point when t is 0. So it's actually starting and ending at the lowest point of 3. Halfway between those, it'll reach its highest point. Okay, so if you look at this, this is actually going to be a reflected cosine function because it's not starting at the midline, it's starting at the bottom. So if it starts at the midline, it's going to be sine. If it starts at the top or starts at the bottom, it's going to be cosine. So I'm going to use cosine this time. So 36 cosine of my b is 4 pi, and then my k is going to be plus 39. Okay, let's look at our next example. Our next example, we want to use a sinusoidal regression. Okay, so for this, I would actually pull out either a graphing calculator or I would go online and use desmos.com/calculator. Okay, and when you're in Desmos, there's a little plus button above where you type everything in. You can click on that plus button and choose to add a table. Okay, and then you can type in all of these values. Type your t's as your x's and the n's as your y's. But what do the t's and n's stand for? This table shows the number of hours of daylight in Denver, Colorado. So this is hometown, right? On the 15th day of each month, where t equals 1 represents January. Okay, so on January 1st, there are going to be 9.68 hours of daylight, or on January 15th. On 2, so February 15th, there's going to be 10.75 hours of daylight. Okay, January, February, March, April, May, June. June 21st is the longest day of the year. So on June 15th, we're almost at the longest day of the year. June 15th, there's going to be 14.98 hours of daylight. Okay, you go 6 months later to December. December is the shortest number of hours of daylight, per day of the year. On December 21st is the shortest day of the year. So this is just a couple days, below that, 9.38 hours of daylight on December 15th. Okay, so if we plug all of these points into Desmos and let Desmos do the plotting for us, we come up with a function like this. Okay, you can see we have January 15th, February, March, April, May, June, and then our days start getting shorter again, July, August, September, October, November, December. Okay, and if we were to add another year, January, February, March, right? June all the way to December, you can see that this definitely has a sinusoidal pattern where it starts at the lowest, increases, decreases, increases, decreases. Okay, so we're going to, in order to find our amplitude and also the vertical shift, we're going to talk very specifically about the longest day the longest number of daylight hours and the lowest number of daylight hours. Okay, so if I take these two values right here and add them together and then divide by 2, okay, so add them and then divide by 2, you're going to find the midline. Okay, when you do that, you find that the midline, K, is approximately 12.18. Okay, if you take these two values and subtract them, right, so the same maximum and the same minimum, and you subtract them, and then again divide that by 2, okay, that's going to give you your amplitude, right? And you find out this time that A equals approximately 2.8. Okay, since this thing starts at the lowest, right, we're going to start at the lowest and then get to the highest and then get back to the lowest. That's actually a reflected cosine wave, right? Instead of starting high, low, high, we're starting low, high, low. Okay, so I know that this A, I need to make A equal to a negative 2.8 in order to reflect my cosine wave upside down. Okay, and then last, let's talk about how long this period length is. Okay, so if I start at the lowest and go to the next lowest, okay, that's going to have a period of 12 months. Okay, that's how long it is. So if we do 12 equals 2 pi over b, I can multiply both sides by b in order to cancel that. So 12b equals 2 pi, and then divide both sides by 12, and those cancel out. So I can find, and if I reduce this fraction, we get that b equals pi over 6. Okay, so what does this look like if we put everything together? We've got an a value, we've got a k value, and we've got a b value. Okay, and what I would really like to type is y equals the a value, so negative 2.8 cosine of b times x. So that's going to be pi over 6, and then multiply that by x, and then move it up. So we're going to have a k of plus 12.18. Okay, so when we graph that, hopefully what it looks like is that it's going up and following this, and then coming back down, and going up, and then coming back down, and repeating that over and over and over, right? The number of daylight hours on the 15th of every month doesn't change from year to year. It increases and decreases from month to month. Okay, so let's look. Let's go over to Desmos and copy a graph and drag it back here. We have graphed y equals negative 2.8 cosine of pi over 6 times x plus 12.18. Okay, and you can see this red line right here. We're going up, right? January 15th, February, March, April. This red line is following my months, my dots of data quite nicely, actually. Okay, so that is how you would apply sine and cosine to repeating patterns that increase and decrease and increase and decrease over time. Thank you so much for watching.